Okay, so hello everyone. Today we are going to discuss about the last part of module number 2.2, that is BJT as a switch and BJT as amplifier, voltage amplifier, and current amplifier also. So that is BJT applications. So let us start. So we consider NP and BJT for our analysis, and here the NP and BJT is used as an inverter and hence as a use as a switch. Okay, so here is my load. The load can be a motor or a LED. It's connected to VCC. From here we take collector terminal, we take the output. All right, input we have applied to the base via RB register, and we have input base current IB. Here the voltages VB and VCE are marked, and the current flowing through the load is IC. Okay, all right, and output is taken from the, as I said before, collector terminal. So NP and BJT in the circuit is switched between the cutoff and the saturation region when it is used as a switch. Okay, that's a very important factor. BJT can be used to switch current, voltages, and power, and that is what we are going to see now. So from here we know that for a fact that if V in voltage, V in applied voltage is lesser than the VB turn on voltage. The VB turn on voltage is VB on, which is around zero point 0.7. So if V in voltage is less than this VB on voltage, your BJT will be in the cutoff mode. All right. So that is what we have written over here. If V in is less than VB on, your BJT is off in the cutoff mode, and in the cutoff mode IB is 0, IC is almost equal to 0. And if that happens, your BJT will act as an open switch and the entire load current will be 0. All right, your output power will be almost equal to VDD. Okay, the power dissipation over here will be 0. And if it is a load is a motor, the motor would be off with a 0 current. If load is a LED, the LED output will be 0 with a 0 current. Okay, LED light output will be 0, it will not be glowing. So in this mode, the BJT is acting as a closed switch. Okay, a switch means on or off. So the BJT is off in this mode of operation, cut off. And um, yeah, so let's try to understand the next part. Now over here, how we wrote this equation from figure number 1, IB can be written as V in minus VB on upon RB. That is what we have written, V in minus VB upon RB. IC can be written as VCC minus VCE upon this load value. I mean this let's consider this load as RC load. Okay, this is a resistive load, so let's consider this as a LED load. So LED load will also have some resistor, or a motor will also have some resistive value. So IC will be given by IC is equal to IC sat is given by VCC. It will be given by VCC minus VCE sat upon RC, where RC is the load value or RL value. All right, and in this case, your V out will be almost equal to VCE sat, which is a very low value. Okay, so if V in is equal to VCC, so in this diagram, if V in is equal to VCC value, your transistor will act as a closed switch. Okay, the transistor will be on and it will be working in the saturation region. So if V in is equal to VCC, your NP and BJT is usually driven into saturation. So when it is driven into saturation, your it behaves as a closed switch. And if it is a closed switch, the voltage across the switch will be very small, and that voltage we call it as VCE sat, and that is around zero point 0.1 to zero point 0.2 volt. It is almost close to 0. All right, uh, yeah, why we have written over here, this should be R. Okay, sorry for that. Okay, this is my load. Yeah, so in this case my output will be driven towards ground, so V out will be very less value. It will be around VC sat when your BJT is acting as a acting as a closed switch. Okay, or it's been driven into saturation. So your current IC will be induced in the circuit, and that will, if load is a motor, the motor will turn on, or the LED, if it is LED, the LED light will glow. So depending upon the type of the load, the motor will operate, or the motor will be on and the LED will be on. Okay, under all this, we have assumed that VBE on is around zero point 0.7. So in summary, VCE when NPN BJT is in cutoff region is equal to VCC, and VCE when NPN BJT is in saturation is almost equal to 0. Okay, that is VCE sat. So from the output characteristics, where is this cutoff and saturation region? Here it is. So this line which we have drawn, red color line, this is called as a DC load line. Some other time, maybe in the advanced course, you will be learning it. It's a intersection of this DC load line with the output characteristics will give it your Q point. So this intersection over here with the family of curves, output characteristics and this DC load line will give it a saturation point. Over here we have IC sat and VC sat. As you can see, VC sat is quite small value. Okay, and here on the right hand side we have VCC equal to VCC comma 0. So here NPN BJT is operating in the saturation region where VC value is equal to VCC. Okay, VC value is almost equal to VCC, but the current is 0. Here VC value is almost equal to 0, but the current is maximum. Okay, so BJT is acting as a switch when BJT will be operating under saturation and cutoff region. Okay, for on and off, for switch to be on and off. Alright, so this is how the BJT will act as a switch. So if they ask you a theory question based on it, this is what you have to explain them. Okay, these 2 pages will be sufficient. Okay, now let us go to the next application, that is BJT as an amplifier. So what is an amplifier? So in an amplifier we are applying a time varying quantity over here V in of t, and output is a amplified form of the input. So voltage gain is output swing upon input swing, which is, if output swing has to be greater than input swing, then we get a voltage gain, and that voltage gain is denoted by AV. Okay, so if the output swing is greater than the input swing, we get an amplified output. Alright. So for NPN BJT to operate as an amplifier, following conditions must be met. We have to create a proper biasing condition for the transistor. That means NPN BJT should be operating in the active region. That means it should be either in, base emitter junction should be forward bias and base collector junction should be reverse bias. So these two conditions should be compulsorily met. And second condition is we have to apply a small time varying input signal. Now look at this diagram. This is the diagram for BJT to work as an amplifier. Let me walk you through it. So at the input side we have a microphone signal. We have superimposed with a DC biasing voltages. Normally this is not the practice. This is just for explanation. I have done it over here. Okay. We never connect input AC and DC together like this, but this is hypothetically to explain the concept ki why, how this is working as an amplifier. Later on we'll show you the modified circuit. Okay, so this is why microphone signal. Okay, microphone signal is V mic of t, that is Vm sin omega t. Very small amplitude, maybe in the range of 10 millivolt, and the sinusoidal signal. Okay, so this is my AC signal. Okay, and this is my DC biasing, because we have to bias the BJT in the proper active region also. So VBV equal to 0.8 will assure that its base emitter junction is forward bias, and VCC equal to 2.5 will, let's consider 2.5. So this will make sure that your BJT is operating in the base collector junction is operating in the reverse bias mode. Okay, so over here we have a load RL. It's in place of RC. We are written here RL, and that value is around 1 kilo ohm. Okay, and output is taken from the collector with respect to ground, where VCE is also equal to V out. We have VBE, we have VCE, and the voltage across RL we call it as VRL. So we know for a fact that your BJT is a current control device. By controlling the current IB, we can control the output current IC, and beta is the current gain of the BJT. And we can say that, let's say that IB current, you know, due to the AC signal and the biasing is around 0.01 milliampere. So IC will be around 0.01 times 100, that will be 1 milliampere. So there is the amplification happening. So in this manner your BJT will act as a current amplifier, because as you can see, output current IC is increasing. IB is the input current, IC is the output current. So it's acting as a current amplifier. Now this IC value being 1 milliampere, let's calculate VRL. So VRL is IC into RL. So that will be 1K into 1 milliampere, that will be 1 volt. So VRL is 1 volt. VCC is 2.5. So how much is VCE? So that will be easier to calculate. VCE or V out will be equal to VCC or V out will be equal to, if you apply KVL, it will be VCC minus ICRL. So VCC minus ICRL, that will be 2.5 minus ICRL, we have done it, it's 1 volt. So it's around 1.5 volt. So VCE will be around 1.5 volt. Alright. So this is the circuit diagram for BJT as an amplifier conceptually. Now let's try to plot the waveform. Remember, everywhere we will have a DC plus AC quantity because we have superimposed them together. So here we have drawn this dotted line as 0.8 volt value, the biasing value for the transistor, and then this small red color one are the small fluctuations from the mic signal. So your V in is nothing but VBB plus V mic. So this mic signal, we microphone signal we want to amplify, which is my AC quantity. This is my DC quantity. Okay, and VRL, we have got to know that its value is around 1 volt, and we will get a slightly amplified value over here, AC quantity. Okay, and why the V out value it's inverted, because as you can see, VC value is VCC minus ICRC. So if the value of VRL is nothing but, what is my value of VRL? VRL is nothing but IC into RL. So as my value of IC is increasing, if IC increases, my VCE is nothing but my V out. So as my value of IC increases, my from this expression, your V out value should reduce, and as my IC reduces, my V out value should increase. So they are inverted. Okay, I mean, if my input increases, my output should reduce. All right. So this is the graph of V out we get over here with the DC value of 1.5, which we have determined over here, and this is my AC amplitude form, amplified form. Okay. So VBB equal to 1 volt and VC equal to 1 volt will make sure that your base emitter junction is forward bias and base collector junction is reverse bias. That will make sure that your NPN BJT is working in the active region of operation. Okay. So here is the same simplified diagram for figure number A. So this diagram can be drawn like this also. So we have a microphone signal superimposed with the biasing condition, and we have output taken from the collector and a load RL connected over there. In reality, this is not how the amplifier is made. We actually use a voltage divider biasing for BJT use as an amplifier. So here is my voltage divider biasing. Actually here what are we doing? We are requiring two power supplies. So in reality we don't require two power supplies. Biasing will make so that from one power supply you derive the other voltages as well. So from one power supply VCC, we will be deriving the voltage VB. This will be my voltage VB, and that VB will be available, with the help of voltage divider R1 and R2. So R1 and R2 forms the voltage potential divider, which will provide the voltage at the base terminal from VCC. So if you calculate by voltage division rule, VB will be R2 upon R1 plus R2 into VBB into VCC. So VB is a fraction of VCC. Let's say VCC is 10 volt, VB will be always less than 10. Okay. So in this way, your base emitter junction is getting forward bias, and VCC is also biasing the base collector region to be reverse bias. Now, as you saw over here, there is a presence of both AC as well as DC quantities. Now, normally, if we are evaluating as an amplifier, as a voltage amplifier, your you would like to see only AC quantities. So we have to block these DC quantities. That is why the role of capacitors over here. Capacitors are well known for blocking the DC value and allowing the AC signal to pass through. So that's the role of input and output coupling capacitors CC1 and CC2. Okay. So they will block DC and allow only AC to pass through. So at this point, for example, let us consider at this point. At this point, if you see, it contains both AC as well as DC. Okay, let me add over here. This contains both AC plus DC. So at the output we'll want only AC, DC will be blocked. So that's the role of your CC2 capacitor. Capacitor will block the DC value and allow the AC to go through. Okay, so that's how we can analyze. So input is a AC, V in is a AC, and output is also a AC quantity. Okay, and output is an amplified form of the input, and that's why we say it's an acting as an amplifier. What about the CE? CE is called as a bypass capacitor. So basically, what happens is all the AC fluctuations should not pass through RE, or else it will reduce the amplification. So what they do is we bypass through the CE. So all the AC fluctuations at the emitter terminal will be going through CE instead of RE. Okay, so your AC fluctuations will be bypassing RE. That's why it's called as a bypass capacitor. Okay, so your voltage divider bias R1 and R2 and VCC supply will make sure that your BJT is operating in the active region of operation. So once BJT is operating in the active region of operation, small time varying quantity signal V in signal will be applicable over here, and it will produce a small fluctuations at the input base current. Those small fluctuations at the input base current will be amplified when it reaches the collector terminal, because IC is beta times IB. So when this current is made to flow through a resistor, that is RC, that small fluctuations will be converted into larger fluctuations, that is terms of IC, and that IC into RC will produce a voltage, and that's how it works as a voltage amplifier. So if they ask you a theory question on how BJT acts as a voltage amplifier, you can explain this conceptually like this. Okay. So yeah, that's it from my side, and with this we complete module number 2.2. That was based on BJT operation, three mode of configuration, that is CC, CB, and CE, and BJT as an amplifier and as a switch. So that's all from my side. Thank you.